All right, guys, so this is going to be lesson 3 and 4. Maybe we'll squeeze 5 in. We'll see how long it goes. So lesson 3 was potential energy diagrams. So these show us the changes in potential energy during a reaction. And we know we have 2 types of reactions. So exothermic right here and exothermic here, endothermic here. Right? So exothermic, we said heat was leaving. We had a negative delta H, and endothermic, heat is coming in. We have a positive delta H. So delta H negative, delta H. Oh, let's go back. Delta H. Too close to the arrow there. There you go. All right. So both of these diagrams, they look a little bit different with the arrows, but all the arrows mean the same thing. So we're just going to go through letter by letter. This might come out looking a little sloppy. We're going to do the best we can. I will post a key for all the letters as well. So let's start with letter A. So I'm going to write them up at the top here. So we have A. That is not an A. That's more of an A. So this is the potential energy of our reactants. And this is the stored energy, right? So how much energy they're holding on to before they get going. So if we look at arrow B on the right-hand side, so on the product side of the diagram, it's in the same position. It's under the curve, right? But it's not, they're different sizes. So this is our potential energy of our products. Right, so same concept, the amount of stored energy in our products. And if we look at line C, in the middle, right here, and here, it goes the whole way from top to bottom. So this is our activated complex. So oh my goodness gracious, this is difficult. So our activated complex. And what this is this is the highest energy point. So this is where our reaction is occurring. This is where bonds are being formed and broken. All right, C, D, so letter D on our reactant side. So this is going to be our activation energy. I mentioned this activation energy. I mentioned this back in the first video when I talked about a catalyst. So the activation energy, this is the minimum amount of energy that is required for the reaction to start, for the reaction to get going. Right, so if we notice exothermic is smaller than endothermic, so it requires less energy for an exothermic reaction to start than it does an endothermic reaction. And then if we look at E, you can see it's similar position and similar setup as D. This is the activation energy of the reverse reaction. So D was activation energy of the forward reaction. Right, so now we're left with F. I'm going to change the color for F just so you guys know which line it refers to. So F is that purple dotted line. This is what our curve would look like if we used a catalyst. So notice how it's lower. We now need more energy to get there and to get that reaction going, but we're still going to reach that same point, that same end point. It's just going to happen a little bit faster, and a lower amount of energy is going to be required. And then I changed the color again for line G. So G is the light blue arrow. So what it's showing you is the 2 dotted lines are just an extension of the potential energy of the reactants and products. So this here is our delta H, right? So this was our H of products, or our potential energy of products, minus our H of our reactants. So this is our heat of reaction. This is going to be that positive or negative number. Let's rewrite that. Our positive or negative number that tells us the type of reaction. Right? We said negative exothermic, positive endothermic. So, potential energy diagrams. Again, I'll post a key with the letters so it's a little bit neater for you guys. Just remember all the arrows and all the positions are the same for both types of reactions. It's just whether or not your starting point is higher or lower and your end point vice versa. That's going to determine the different types of reaction that you're working with. So that's lesson 3. Lesson 3 is pretty brief, just the potential energy diagrams. Now we have lesson 4. Erase my little marks over here. Lesson 4. This is our equilibrium. So equilibrium. Things are equal, right? So this is occurring when our forward reaction and our reverse reaction occur at the same time. And we're going to use a double arrow for this. So typically you'll see it written like this, like 2 half arrows, or you'll see like a double-ended arrow, or you'll even just see 2 arrows. It doesn't matter. It's all the same. It means that the forward and backwards are both happening. The reaction can go in either direction. So again, equilibrium, things are equal. So the rates of reaction are equal. So the concentration of products and reactants don't have to be equal, just that the rate of the reactions are the same. And equilibrium we call dynamic. You might also see it written as dynamic equilibrium. And this is just saying that it's constant. It doesn't stop. So the reaction might look complete, but really what's happening is the forward and backwards, the forward, I'm trying to write with the eraser feature. The forward and backwards reaction are occurring at the same time. So that's the general idea behind equilibrium. There are a couple factors that affect equilibrium, which we'll talk about in lesson 5. So right now we're going to talk about 3 different types of equilibrium. And our first type of equilibrium is going to be phase equilibrium. So the key thing here is remember phase equilibrium, phase change. So this is occurring at our phase change. If you remember your heating and cooling curves, our phase changes here are the flat parts, right? So solid to liquid, liquid to solid, liquid to gas, gas to liquid. So notice how those parts are flat. That means at that temperature, for that amount of time, they're existing at the same rate. So if you boil a pot of water and you put a lid on it, right? You see all those condensation bubbles, all the water on top of the lid. What's happening is the water that's a liquid is boiling and becoming water vapor and then going back down to water, and that's constantly going until you take that top off, right? So remember that phase equilibrium is occurring at phase changes. So this should have an arrow here. When I transferred this over from PowerPoint to the app I'm using, it didn't do some of the symbols. So these are the flat parts of our heating and cooling curves, all right? So key takeaway here, phase equilibrium, phase change, all right? So solid to liquid, liquid to solid, gas to liquid, liquid to gas. Okay. Our other 2 types of equilibrium, we have solution equilibrium. This occurs when a solution is saturated. Remember we talked about table G? I'm going to write it up here just so everybody remembers. Table G, when it was on the line, it was saturated, right? I mentioned equilibrium when we were talking about this back in the solutions unit before we were self-isolating. When it is saturated, it is happy. It is equal. The rate of dissolving is equal to the rate of recrystallization. So the rate of a solid to aqueous is equal to the rate of aqueous to solid. So for this one, I would remember color. I remember solution, saturated. That's how you're going to remember the equilibrium, right? If it's unsaturated or supersaturated, it is not at equilibrium. It's not stable. The forward and backwards reactions are not at the same point yet. And our last type of equilibrium, we have chemical equilibrium. This is just occurring when the rate of the forward and the rate of the reverse are equal. Remember, concentration of reactants and products don't need to be equal, just that the rates are constantly moving forward and backwards at the same rate. So I still have time, so I am going to incorporate lesson 5 into this video, and then I'll make a 3rd video with the worksheet answer keys and kind of talk about those as well. All right.